Have you ever just looked at a glass of water, or even the air you're breathing right now, and thought, what's the secret recipe here? What is this stuff really made of? Well, that's pretty much what chemistry is all about. It's like being a detective figuring out the exact ingredients for, well, everything. And today, we're going to crack that code. All right, so let's get right into it with a big question. We all learn in school that water is H2O, right? But think about this for a second. How do we actually know, for a fact, that it's made of exactly 88.89% oxygen and 11.11% hydrogen by weight? You can't just pick up a single water molecule and pop it on a scale. It sounds totally impossible, doesn't it? Well, spoiler alert, it's not. So to figure this all out, we're going to build what I like to call a chemist's toolkit. We've got 4 sections ahead. First, the ingredient list. Then, Avogadro's big idea. After that, weighing the invisible. And finally, we'll look at your new toolkit. Basically, we're going to learn how to find the ingredients, count them, and even weigh them. Let's do it. All right, first up, the ingredient list. We're going to be finding a molecule's recipe with something called percentage composition. This is our first tool, and it's all about figuring out the exact breakdown of, well, anything. So what is percentage composition? It's the percentage by mass of each element inside a compound. And here's the key thing to remember. This is all about weight, not about counting atoms. It tells you, hey, for this molecule, what slice of the total weight comes from carbon? What slice comes from hydrogen? It's like a pie chart, but for chemicals. Okay, to really get this, let's look at an example. We're going to find the recipe for methane, which you might know as simple natural gas. Its formula is CH4. And that formula is super helpful. It's telling us right away that we've got 1 carbon atom and 4 hydrogen atoms to play with. And check this out. The math here is actually pretty straightforward. We just need to know the atomic mass of our building blocks. Let's keep it simple and use rounded numbers. So carbon has a mass of about 12, and hydrogen is about 1. We've got 1 carbon atom, so that gives us a mass of 12. And we've got 4 hydrogen atoms, so that's 4 times 1, which is 4. Just add them up. 12 plus 4 gives us a total mass for the whole methane molecule of 16. And boom, here's our recipe. To get those percentages, we just do a little division. The carbon part was 12, right? So 12 divided by the total of 16, that's 0.75, or, 75%. And for hydrogen, its total mass was 4. So 4 divided by 16, that's 0.25, or 25%. And just like that, we found the exact chemical recipe for methane. Pretty cool, huh? Okay, tool number 2, Avogadro's big idea. This is all about how to count molecules by measuring volume. So we figured out the what in the recipe, but now for the how many. Molecules are so tiny, they're basically invisible. How in the world do you count them? Well, a brilliant Italian scientist named Amedeo Avogadro had a flash of genius. And this is his big idea. He said, equal volumes of all gases under similar conditions of temperature and pressure contain equal number of molecules. It sounds a little formal, but honestly, it's so simple and so powerful. This was a huge leap for chemistry. What he's saying is, look, if you just keep the temperature and pressure the same, the amount of space a gas takes up, its volume, tells you exactly how many molecules are in there. It was a genius trick to count the uncountable. Let me break it down with an analogy. Let's call it the magic measuring cup. Imagine you have 3 boxes, and they're all exactly the same size. Now, you fill the first box with hydrogen gas, you fill the second with oxygen gas. Avogadro's law tells us that it doesn't matter what gas you use. As long as the boxes are the same size and at the same temperature and pressure, they will all hold the exact same number of molecules. It's wild, right? And this isn't just a thought experiment. It's incredibly useful. Take a real reaction, like hydrogen plus chlorine, which makes hydrogen chloride. You can literally measure this. You take 1 scoop or 1 volume of hydrogen, add 1 volume of chlorine, and you get out 2 volumes of hydrogen chloride. Because of Avogadro, we can now say with confidence that some number of hydrogen molecules plus the same number of chlorine molecules gives us twice that number of hydrogen chloride molecules. We're literally reading a chemical reaction just by measuring space. All right, time for our third and final tool in the toolkit, weighing the invisible. This part is about using something called vapor density to compare how heavy molecules are. So we can figure out the recipe, we can even count the molecules, but how do we weigh them? How do you weigh something that's basically weightless? Well, you don't. You compare it to something else. So there are 2 main ways to talk about the weight of a gas molecule. On the one hand, you have relative molecular mass. This compares a gas molecule to the lightest thing we can think of, a single atom of hydrogen. But then there's vapor density. This compares that same gas molecule to a full molecule of hydrogen, which is actually two atoms stuck together, so we write it as H2. And that right there, that's the secret sauce. The key difference is that a hydrogen molecule has two atoms. That's it. That's the whole trick. This means that our measuring stick for vapor density, the H2 molecule, is exactly twice as heavy as our measuring stick for relative molecular mass, the single H atom. And because of that, we get this perfect, super useful relationship. So it all boils down to this magic number, 2. Because our vapor density yardstick is precisely twice as heavy as our other one, it means the relative molecular mass of any gas is always going to be exactly twice its vapor density. It has to be. It's that simple. And that gives us this beautiful final formula. Relative molecular mass equals 2 times vapor density. That's the big payoff. All that thinking about atoms versus molecules leads us here. If you can figure out the vapor density of a gas, you just multiply it by 2 and bam, you've got its relative molecular mass. We just figured out how to weigh the invisible. And there we go. We've just built our new chemistry toolkit. Let's put it all together and do a quick recap of what these amazing tools can do. So here's what's in our toolkit. First, percentage composition. This tells you the what. It's your ingredient list for any molecule. Then you've got Avogadro's law. This tells you the how many. It's that magic measuring cup for counting molecules just by looking at volume. And finally, vapor density. This tells you the how heavy. It's our clever way of weighing molecules by comparing them. The what, the how many, and the how heavy. You've got it all. You know, these 3 ideas, they're really the foundation of so much of modern chemistry. They let us understand everything from a simple drop of water to the most complex medicines. So now you've got the tools. The only question left is, what chemical recipe out there in the world would you want to uncover next?